is Arjun Kar.
Let me try sharing my screen.
Yeah,
Can
Arjun
everybody
is
see that?
talking about deep learning, knot invariance, and gauge theory. Again, about knots, I think. And Arjun, please go ahead. Thanks.
Yeah. Okay. Yeah. Thanks very much for the invitation to speak here. I'm going to be telling you about some recent work that appeared earlier this month. It's based on this paper. It's joint work with Jessica Craven, Mark Hughes, who just spoke, and Vishnu Jejula. And I really want to highlight the great work that Jessica did on this project. She's a master's student currently, so look for her PhD application. Okay, so as you heard in the last talk, knots are just embeddings of some circle in a three-dimensional space. And one of the most fundamental problems in knot theory is knot comparison. So given two-dimensional knot diagrams, which are just some projections to a plane, how can we tell if they represent the same knot? So these two knot diagrams look naively very different, but perhaps there's some way to move the strands around each other so that you turn one of them into the other. So since I'm asking the question, it probably won't surprise you that these two diagrams actually represent the same knot. But what may surprise you is that neither of these knots are actually non-trivial. So both of these knots represent the perfectly unknotted circle. So you can understand that it's useful to have a way to tell different knots apart. So to help us with this problem, we compute topological invariants. So if two diagrams yield different invariants, then they represent different knots, but not necessarily the other way around. So one type of invariant is called the knot complement manifold, which is just constructed by drilling out solid torus neighborhood of the knot embedded in the three-sphere. But you can imagine that this is not a very useful invariant. Somehow you don't get much more information out of this knot invariant than if you just have the diagram of the knot itself. So understanding relationships between invariants is an important question in knot theory, and such relationships are often associated with important open problems. So Mark mentioned in his talk the Jones unknot conjecture. There's another conjecture called the volume conjecture, which relates a certain family of algebraic invariants to the hyperbolic volume of the knot complement. So that invariant that I mentioned on the last slide sometimes admits a complete hyperbolic metric, and the volume of that object turns out to be a topological invariant of the knot. And there's another conjecture called the smooth four-dimensional Poincare conjecture, where one approach to that problem involves a knot invariant called the slice genus, which Mark also talked about. And that's a difficult to compute geometric quantity for which the existence of even a bound by an algebraic invariant is useful. And we will discuss such an algebraic invariant in this talk. On the physics side of things, these relationships, in particular in the volume conjecture, they're often associated with subtle phenomena in topological field theory or string theory. And prior work demonstrated that in some cases, these relationships can be efficiently machine learned. So what I want to do today is review some relevant knot invariants and the gauge theory that underlies them, and then talk about machine learning correlations between these invariants. And finally, I'll talk about some analytic explanations. So before going on, I want to emphasize that this third point is really a work in progress. We do not have concrete analytic explanations of everything that we're finding. And that's partially because we think what we're finding is really novel. It's a novel correlation that is unexpected and very interesting. So the Jones polynomial is what we'll start with. It's a very useful and important knot invariant, and it's a Laurent polynomial with integer coefficients obeying this recursion relation that you also saw in Mark's talk. And we normalize the Jones polynomial so that the unknot has Jones polynomial 1. So just as an example, the simplest non-trivial knot is called the trefoil knot, and it has Jones polynomial, which I've written here. So physicists may be more familiar with this object through Chern-Simons theory, so I'll just review that briefly. So the Jones polynomial, in particular, its evaluations, are expectation values of a Wilson loop operator that you place along the knot in SU2 Chern-Simons gauge theory on the three-sphere. So here's the Chern-Simons action. A is the gauge field, and this UN is the Wilson loop operator of this theory, and N represents the dimension of the SU2 representation, the dimension in which we take the trace. So then the statement that's made in this paper is that the Jones polynomial in what's called the N-colored representation is evaluated at this particular phase, so it depends on an integer k, and that is equal to this ratio of path integrals. So on the top, we have the path integral with the Wilson loop insertion, and on the bottom, we just have the normalization by the unknot. You can see the coupling is appearing here in the action. Now, the original Jones polynomial that I described on the previous page corresponds to taking the Wilson loop trace into fundamental representation. So you take the two-dimensional representation of SU2. Now, another invariant that will be useful for us is the categorification of the Jones polynomial. And that sounds very fancy, but it's fairly simple. It just means that there's a bigraded cohomology theory. You should think of this H as some vector space for which J is the graded Euler characteristic. So this was shown by Kovanov, and this H is sometimes called Kovanov homology. So the relevant formula is here. So this H is some vector space, and it's graded. So it carries a grading M, which is sometimes called the homological grading, and N, which is sometimes called the quantum grading. And the story is that you're supposed to compute this particular sum over the different groups and weighted by their dimension, and that's supposed to produce for you the Jones polynomial on the left-hand side. So H is often presented in tabular form, and for the trefoil knot, here it is. So you can see that there are only 4 non-zero vector spaces in this Kovanov homology. They correspond to homological grading 0 with quantum gradings 1 and 3. And there are 2 other non-trivial groups at homological grading 2 and 3 and quantum grading 5 and 9. So in gauge theory, the situation is a bit less clear. It has not been proven that this H may be computed using gauge theory, but there is a proposal that it's the cohomology of a certain supercharge operator Q in the 6-dimensional 0,2 theory on a certain Cauchy slice, with a surface operator inserted that I'll call sigma k, and the topology of this surface operator is set by the knot k. There's an equivalent, though less powerful description, because it's not ultraviolet complete, through the Q cohomology in the Hilbert space of 5-dimensional super-Yang-Mills theory, where the bigrading is generated by a U1 cross U1 symmetry that's associated to the fermion and instanton number operators, respectively. So the fermion number operator is supposed to generate the homological grading on the ground states, and the instanton number operator is supposed to generate the quantum grading. Now, for the specialization that yields the Jones polynomial, there's an equivalent 4-dimensional super-Yang-Mills path integral, which counts classical supersymmetric solutions weighted by this factor, -1 to the f times q to the p, where f and p are the fermion and instanton numbers of the classical solution. And this gives a 4-dimensional interpretation of the Jones polynomial, which was originally a 3-dimensional invariant. So 2 other non-invariants, which will be important for us, which in a certain sense are naturally 4-dimensional, are the Rasmussen S invariant and the smooth slice genus, which I'll call S and G respectively. So the S invariant has a rather complicated definition. It's defined using a certain spectral sequence, which collapses the Kovanov homology to Q plus Q, which is sometimes called Lie homology. And the 2 remaining factors were shown by Rasmussen to have instanton grading S plus or minus 1 for some integer S, and S is called the Rasmussen S invariant. Now, the smooth slice genus of a knot is the least integer G, for which there's a smooth surface sigma that sits in the 4-ball, and it has a boundary. This surface sigma has a boundary that lives also on the boundary of the 4-ball, and the boundary of the surface is topologically the same as the knot. So as another example, the trefoil has Rasmussen S invariant equal to 2 and slice genus equal to 1. So neither S nor G have simple gauge theory interpretations, though there's some work that suggests that the Rasmussen invariant may be accessible through certain supercharge deformations. And one other fact which will be important for us is that there is sometimes a more direct connection between Kovanov homology and S than the spectral sequence. Though it's false in general, it can be proven for certain small classes of knots. It's called the night move conjecture. And this provides a formula for S in terms of what's called the Kovanov polynomial, which I'll denote as KH. It's a function of 2 variables. The Kovanov polynomial is just given by the same sum which produces the Jones polynomial, but instead of -1 weight in the homological grading, we allow it to be some general variable t. Then the night move conjecture states that if you replace t with -q to the -4, the resulting polynomial that you get is related to S in a very simple way. So it's just q to the S times this combination, q plus q inverse. So it's worthwhile to understand what sort of information is contained in the Jones polynomial and Kovanov homology. So Rasmussen proved a general inequality where the magnitude of his invariant is less than or equal to twice the slice genus. So that relates these two. But perhaps the Jones polynomial and Kovanov homology know more about S and G than is obvious. So that's where our machine learning experiments come in. So we performed 4 classes of experiments using a simple 2-layer neural network with 100 hidden units per layer. So the input to the network was either the Jones polynomial or the Kovanov polynomial. So we flattened these into vectors. And the output was either the Rasmussen S invariant or the smooth slice genus. Now the outputs are integer valued, so we set up a classification problem where the number of classes was equal to the number of possibilities in the data set. So here's a small cartoon of the network. Here's the input layer where we feed in the Jones polynomial or the Kovanov polynomial. We had exactly 2 hidden layers, and the output layer consists of the different classes, the different possible S invariants or slice genus. So the data set that we use consists of roughly 500,000 knots, and due to the difficulty of computing the slice genus, the data generation process was actually a bit complicated. So let me describe how that goes. So we began with 2 groups of seed braids. So the first group was the knot info data set, which is about 1,200 knots that all have known slice, that mostly have known slice genus, and also random quasi-positive or quasi-negative braids. Now those are braids of this form, where alpha is some braid word, and then there's a sigma I, another single braid group generator, and another alpha. And these have known slice genus by the slice-Bedekin inequality. So the purpose of starting with these 2 groups is essentially that we need to begin at a place where we know the slice genus, because it's very difficult to compute in general. So then the goal is going to be to generate a bigger data set using these 2 seed data sets. So given a seed braid that I'll call beta, we randomly inserted words of this form, quasi-negative and quasi-positive words, into beta. So each such insertion changes the slice Euler characteristic by a bounded amount. It's actually either plus minus 1 or 0, which together with the known initial slice genus gives upper and lower bounds on the final slice genus. So this procedure gives us a large data set where for every knot in the data set, we have some bounds on what the slice genus can be. We don't know its exact value though. Then a final sequence of Markov moves further randomize the data set, just to throw a little bit more complicated generation procedures in there. So as I was mentioning, we don't actually know the slice genus yet, but computation of other invariants was enough to completely fix the slice genus for many of the knots. So one example of such a procedure was using this software called KnotJob. We computed the S invariants and then used Rasmussen's inequality. So we used the inequality that the magnitude of S should be a lower bound on twice the slice genus. And this was sometimes enough to fix the slice genus completely. Then a smaller data set was generated using the random petal permutation model, but the slice genus for these is hard to compute, and so we excluded them from slice genus experiments, but we could compute their S invariants. So they were included in experiments that involved the Rasmussen invariant. So in total, we used about 535,000 knots, and for all of these, we knew the Jones polynomial, the Kovanov polynomial, and also the Rasmussen invariant. And we knew the slice genus for about 440,000 of these. So we were able to determine the slice genus for quite a large proportion of the total data set. Now, despite the careful construction, there are actually no known exact relationships between these invariants in our data set, other than the night move conjecture, which we checked holds for the vast majority of our knots. So I'll just reproduce that here. So given the Kovanov polynomial, it's very conceivable that the network will understand what the Rasmussen S invariant is, because there's a very simple formula relating the 2. All right, so here are our results. So we found that the network predicts the Rasmussen invariant and the slice genus with over 98% accuracy from the full Kovanov polynomial when trained on about 25% of the data set, but these accuracies do not drop below 94% when the training fraction is just 1% of the total. And we also trained the network on specializations of the Kovanov polynomial. So instead of t, we input minus q to the n for various n, and we tried to predict the S invariant and the slice genus. So you can see that the network does very well for any value of n, but it does particularly well at n equals minus 4. And that's pretty believable because of the night move conjecture that I mentioned on the previous page. So there's a simple formula when n is equal to minus 4 that explains why the network performs well. But it also performs extremely well at n equals minus 2. And this is a bit harder to explain. So I'll talk about that shortly. But let me just finish giving you the results of the machine learning. So when trained on the same fraction, the network achieves 95% and 96% accuracy, respectively, in predicting the Rasmussen invariant or the slice genus from the Jones polynomial. When the training fraction is decreased to 1% of the data set, the accuracies are still pretty close to 89%. We also evaluated the Jones polynomial. So using some intuition or inspiration from Chern-Simons theory, we evaluated the Jones polynomial at some roots of unity, and we assembled a vector for each k with values in this particular range, and we trained the network with that as input. And we actually found that the network is still able to predict the Rasmussen invariant and the slice genus to fairly high accuracy, over 90% in all cases. Okay, so the upshot of all these experiments, and you can see the paper for much more analysis, is that there's a robust correlation that exists between the Jones polynomial or the Kovanov polynomial and the Rasmussen S invariant or the slice genus. Now, the slice genus correlation is very difficult to explain. There's no known simple formula to extract it from the Kovanov homology, and certainly not from the Jones polynomial. But on the other hand, the S invariant has a clear definition from Kovanov homology, so we can try to look for analytic explanations of that correlation. So let me turn to our attempts at analytic explanations. So as I was mentioning before, the correlations between the full Kovanov polynomial or the n equals minus 4 specialization and the Rasmussen S invariant are simply explained using the night move conjecture. But the strong performance at n equals minus 2 was much more mysterious. So by just looking at some of these polynomials, we found that this particular specialization of the Kovanov polynomial often takes a form which is completely fixed by the Rasmussen S invariant. So just like the n equals minus 4 polynomial was completely fixed by it, we found that the same holds true for n equals minus 2, but it's not the same form. So here's an example of a formula. So you can see that there are two terms in this formula, and it looks very, very similar to the n equals minus 4 specialization, but the coefficients are different. The coefficients are not unit, as in the n equals minus 4 specialization, but instead they depend in some determined way on the Rasmussen S invariant. And this formula is not the case for all knots in the data set. There are also cases where this specialization has 3 terms, or there are other cases where there are even more terms, but here's the 3-term formula. So you can see that now the powers that appear in the specialization depend in a controlled way on the S invariant, but so do the coefficients. So for example, the q to the S minus 1 term always has coefficient minus 1. And the other terms are determined by the S invariant as well. So in these formulas, we know how to explain for a given knot which powers of q will appear and how many terms the formula will have. And this comes from a substitution where we send t to t times q to the minus 2. In some sense, this renormalizes the fermion gradient before setting t equals minus 1, which fixes the powers and the number of terms that can appear in terms of the instanton gradings at order 1 in t, which are related directly to the S invariant for most knots in our data set. Now, the coefficients, on the other hand, cannot be so simply explained, and their complete determination by the Rasmussen S invariant suggests that perhaps this invariant is encoded in Kovanov homology in more than one way. Specifically, it's not just the instanton number which may yield the S invariant, but also the total appropriately graded number of supersymmetric ground states in the 5D Superyang-Mills description. So the correlation of the Jones polynomial with S is even less understandable. It's common lore in knot theory that the S invariant captures information which is distinct from the Jones polynomial. And indeed, there are knots with identical Jones polynomial, but different S invariants. So there cannot be a precise formula for S which uses only the Jones polynomial. Now, the gauge theory statement of this connection, which we're currently exploring, is as follows. The correspondence between Kovanov homology and the supercharged cohomology in the 5D Superyang-Mills arises by essentially applying stringy dualities to the four-dimensional n equals 4 theory on this particular manifold with a not defect on the boundary. So this R plus is array, it has a boundary, and you place a not defect there, and the path integral of this n equals 4 theory is supposed to produce the Jones polynomial for you. It's equal to the three-dimensional Chern-Simons path integral on its boundary by supersymmetric localization. But the catch is that this three-dimensional Chern-Simons path integral possibly has an exotic integration cycle. So it's not the case that you always get the typical integration cycle of Chern-Simons theory. So this correlation between the Jones polynomial and S points to an appearance in three dimensions in the three-dimensional Chern-Simons theory of some specific information about approximate supersymmetric ground states in the five-dimensional theory, which arises by looking for a Hilbert space formulation of the four-dimensional path integral. And so the conjecture, the rather admittedly vague conjecture that we would like to make, is that the space of exotic integration cycles in the three-dimensional Chern-Simons theory has privileged access, where I'm not being specific with what I mean by that, but it has some sort of privileged access to the instanton numbers of approximate supersymmetric ground states in the five-dimensional theory, specifically with fermion number 0. So in our data set, these ground states with fermion number 0 are the ones that determine the S invariant. And in favorable cases, the space of integration cycles may actually determine the instanton numbers completely. So we're currently exploring this conjecture by trying to understand the necessary deformation of Kovanov homology to derive the S invariant in the five-dimensional language. All right, so what have we done here? We've trained a neural network to learn some robust correlations between the Jones or Kovanov polynomials and the Rasmussen S invariant or slice genus. And these correlations persist even when training on just 1% of the data set. We have partial analytic explanations for the Kovanov correlation with the S invariant and a very rough conjecture for a gauge theory story that approximately relates Jones polynomial and the Rasmussen invariant. The correlations with the slice genus, though, remain very mysterious, and perhaps they suggest some kind of algebraic formula for the slice genus. So as a final note, let me just say a bit more about that. So in a previous work with Jessica and Vishnu, we found that a correlation between the Jones polynomial and hyperbolic volume could be explained by using exotic integration cycles for three-dimensional Chern-Simons theory. Now, the hyperbolic volume is also not determined by the Jones polynomial. So two knots can have the same Jones polynomial, but different hyperbolic volumes. So there can be no precise formula relating the volume to the Jones polynomial. But understanding the gauge theory mechanism for this, which we were able to do in this paper, building on some previous work of Witten, it leads one immediately to the celebrated volume conjecture, which relates the generalizations of the Jones polynomial, the so-called colored Jones polynomials, to the hyperbolic volume. And this volume conjecture really does have a chance of being true. So we were led to a conjecture which has been quite influential.
You have 5 more minutes.
Thanks. So just speculatively, if we can find a similar gauge theory mechanism for the effect we're seeing here, whether through gauge symmetry breaking, supercharged deformation, or some other effect, is it possible that we could be led to something like a slice genus conjecture or an S invariant conjecture, this time relating some similar three-dimensional algebraic invariant, perhaps the Jones polynomial and its generalizations, this time to a four-dimensional geometric invariant, rather than a three-dimensional invariant like the volume? Let me stop there. Thanks. Okay, I think Fabian has a question.
Yeah. Thank you very much. So I have a question. After me, Sergei Gugov also has a question. I'll start. It's a very simple. Yeah, so I have a very simple technical question. Can you explain how you encoded the Kovanov or the Jones polynomial for input for your neural network? Because these are kind of sparse, and then you get a lot of zeros. What did you do there?
Yeah, good. So the Jones polynomial was encoded in this coefficient and power style. Yeah. So we encode the coefficient first and then the power. Yeah. So you flatten that into a vector, and we pad with zeros on the right.
So the sparsity was not a problem here?
Sorry?
The fact that this is kind of sparse didn't present a problem. How many crossings did you, or how large was the range that you had?
Yeah, so the crossings that we had went up to maybe 35 or 40 crossings, not much higher than that. Sparsity Yeah, let's see. I don't remember the exact length of the final vectors. Maybe one of my collaborators wants to comment on that. But I don't think sparsity presented a problem for us. No, the Kovalov polynomials were encoded in a similar way. So we encoded the power of t, the power of q, and the coefficient.
Thank you.
Yeah.
Thank you for the nice talk. I actually have a couple of questions, if it's okay, about
Yeah.
particular physics aspects. So in the past 10 years or so, it's been a major challenge to either define or compute S invariant using gauge theory approach. Are you saying that you have a solution to this problem? Because as far as I know,
yeah, no, we are not saying we have a solution to this problem. Yeah.
So then what is the, I'm a little lost. So what's the content of the statement about gauge theory? What's the substance?
Yeah, so so what we can say is that, so I mentioned this night move conjecture. So this conjecture, which is false in general, holds for most knots in our data set. And in this case, there is a formula in gauge theory that computes the S invariant. It just comes from a specialization of the trace over the ground space, over the space of ground states in the 5-dimensional Superyang-Mills theory.
But it's not using gauge theory. It can be used in any other formulation of Kovalov homology, right?
That's right.
How did you use gauge theory here? I'm confused. So there are about 10 different formulations of Kovalov homology based on combinatorics, geometric representation theory, enumerative geometry. So are you saying that only from gauge theory you can see this, or?
No, presumably it's possible to see in other formulations also of Kovalov homology. Yeah.
But I mean, did you really use gauge theory moduli spaces or just general properties that come from combinatorial formulation of Kovalov?
No. There was nothing really about gauge theory that we used here except the path. So there's a formula for the path integral. So the path integral of this 5-dimensional Superyang-Mills theory is supposed to produce for you, at least in the zero energy sector, the Kovalov polynomial. And the statement is that this specialization of the Kovalov polynomial is going to yield the S invariant for you.
I see, but that's also true in any other formulation. So
it's also true in any other formulation. That's right. Yeah.
I see. So thank you for clarifying this. So then following up on this, one formulation which is extremely useful in explaining all kinds of relations, in fact, several generalizations that you found where you have more terms, is based on not-Weber correspondence. So that's a very powerful machine that encodes many relations. Have you tried to think about it?
No, we haven't thought about that yet. At the moment, actually, we're trying to understand your paper on BPS sequences, sequencing BPS spectra. So that is using these 2-dimensional Landau-Ginzburg models, and we'd like to understand how that sort of symmetry breaking pattern that you use to extract Lie homology appears in this 5-dimensional gauge theory, but we don't currently have a good enough understanding of how that works.
Yeah, that's what I referred as a major challenge. I thought about this for 10 years and I still don't know how to do it. But I think not-Weber correspondence could be extremely useful.
I see. Okay, thanks.
I actually have a question following up on that, if you don't mind. So this night move conjecture holds some fraction of the time on your knots for many of them. And then you have neural networks performing quite well in the S invariant. Have you tried to, and then furthermore, you also have the n equals -2 results where you have analytic things that are not related to the night move conjecture. Have you tried to sort of subtract off the night move conjecture instances, or alternatively, how does that 98% compare to the fraction that satisfied the night move conjecture? Is it just reproducing the night move conjecture, or is it doing more?
Yeah, that's a very interesting question. So we haven't tried to subtract off from the data set the knots which obey the night move conjecture. Yeah, it's an interesting question to determine. As far as we can tell, so here are the n equals -2 formulas. These formulas don't seem to be implied by the night move conjecture. So at least we can explain the powers which appear, but the coefficients, we don't have a good understanding of why they're determined also by the S invariant. It would be interesting to see if a formula like this holds even in a case when the night move conjecture fails.
Another simple question. I mean, you were getting high 90s type accuracy on the S invariant. Is the fraction of your instances that satisfy the night move conjecture, is it also high 90s, or is it more like 70, so that you know? That...
It's also high 90s. Yeah.
It's also
So so it really is most of the knots in the data set that satisfy the night move conjecture.
Thank you. Nice talk.
Thanks.
Any more questions? Don't see any more questions. So let us all, if there is no question, then let us all thank Arjun. Many thanks for your wonderful talk. And let us go to the discussion session.